Welcome to my science tutorial. In this video we are going to have an introduction to aromaticity. You probably would have heard aromatics before, and it's talking about compounds that have these nice smells like vanilla or cinnamaldehyde. Yeah, so let's look at some properties. Over here we say aromaticity is a chemical property of benzene and its derivative and certain type of pi system. Certain types of pi system. This pi system is talking about pi bonding in the benzene. So what are the okay, we have benzene here. We have benzene here. And so most of the compounds we'll be looking at will have benzene-like structure inside them. Not necessarily benzene, but will have this kind of pi system in there. So we have properties of aromatics. The first we can talk about is their unusual stability. Unusual stability. So we found out that there are other compounds like benzene. There are alkene compounds. They have this pi system conjugated, but they are not stable compared to benzene. So in some books we find out that aromaticity is the highest state of stability that any compound can have. And then another thing is they have what we call diminished reactivity. Diminished reactivity. So what is diminished reactivity? We'll be looking at it soon. So another thing is number 3, we have unexpected products. Unexpected product in the sense that anytime we have these aromatic compounds reacting, they give products that we least expect, and then we'll look at that soon. So unexpected. Products. Alright, so I mentioned benzene, so we have benzene as an example. We also have toluene. We have toluene in there. So if you take your favorite aroma like vanilla, and this is the structure of vanilla. This vanilla. It's a benzene with so we have a benzene here. Double bonded O. We have this hydroxy group here, OH, and then our ethoxy group over here. This is vanilla. We have other ones like cinnamaldehyde, that is from cinnamon. It's really simple structure. We have our benzene, and then this is double bonded to oxygen, and then alright then. So now let's look at naming of substituted benzene. In this tutorial or this course aromaticity, you probably see you'll be seeing a lot of benzene like products. You have benzene, and then you have most reactions where you have elements like chlorine or bromine, halogens, sulfuric acid molecules and stuff getting attached to benzene. So let's look at how we name these compounds. So we have benzene here. We have a benzene. So let's say this is what we originally have attached to the benzene. So let's call this X. If we number this 1, 2, 3, 4, 5, and this is 6. And this position over here, okay, let me draw this here again. Let's pick a different color. If we have this benzene over here, and this position we can call it auto. Over here we have what we call the meta position, and this is para. And then don't forget this position 1 and 5 is the same here, so over here this is also auto. And we have our meta here at position 4 too, meta. Alright, so anytime you have a compound, so when we talk of a compound like toluene is like this. It's just a benzene with a metal attached to it. So there's a benzene ring, and then we have a metal group, CH3. Alright, so this is our toluene. If we have a chlorine attached to this Cl, we can say this is an autochlorotoluene. Or if we have a bromine here, we can say that the bromine is at the para position and the chlorine is at the auto position. And what about this position? You probably know it. There is a meta position. Alright, so when we start looking at a lot of example, we will find a lot of compounds having these things attached to these positions that we just talked about. Now let's look at evidence of diminished reactivity. What this simply means is that benzene or aromatic compounds will undergo reactions under special conditions, and this is what we are referring to as evidence of diminished reactivity. Alright then, so if we take a compound, or let's say alkene compounds like cyclohexene, this is cyclohexene. Any other cyclohexene probably will undergo a reaction with chemicals like H2SO4, and that is what we get. We have this, and then oxygen attached to SO3H. So we'll have this alkene double bond breaking up, and we have hydrogens attached here, and here. And this can also undergo a reaction with bromine, Br2, and I will have this product here. Bromine, hydrogen, as well as reacting with strong oxidants like KMNO4, potassium permanganate. And this will oxidize this product to give us carboxylic acid, so we have this CO2H. So these are reactions that any other alkene will undergo easily, but if you take an aromatic compound, like I'm using benzene because basically most of the naturally occurring aromatic compounds we have benzene in there. These aromatic compounds will not just react with any of these chemicals, like H2SO4, potassium permanganate, or bromine, or any halogen. And this is what we are referring to as diminished reactivity. So it requires special conditions. So if you take a benzene, benzene reacting with Br2, we have to treat it with FeBr3 before we will be able to add a bromine to this benzene. Not only that, we also need heat. So these are the special conditions under which we add a bromine to benzene, or formation of bromobenzene. So you find out that comparing this to the cyclohexane, which is an alkene, we don't require any of these special conditions such as heating up the reaction system or adding FeBr3 before adding bromine to this position of benzene. But then if you look at the benzene, these conditions are necessary to form these products, and that is basically what we're referring to as diminished reactivity. So if you take something like H2SO4, cyclohexane, we just have this adding up bar. We are talking about aromatics, no, it's not going to work, so we need to heat this up. We add heat, and then we get this attached to our benzene. So we have SO3H. All right. Now we are looking at evidence of the unusual stability that we have in aromatic compounds. And basically, one thing that gives them a lot of stability is what is known as resonance energy. So let's say resonance energy. Resonance energy basically is, we can see it is a measure of the extra stability of any aromatic or conjugated system when we compare this to the corresponding number of isolated bonds or any other compound which is not an aromatic. So we measure that, or let's just say we can say that it is the expected energy that is unavailable in an aromatic compound, and we are good to go. And so we have a lot of other things like resonance itself, and then over here we have resonance energy, we have resonance itself, and then we can also talk about conjugation. And there is something also known as Haeckel's rule. Now don't worry about this, we are going to look at all this in our next tutorial, so just check our playlist, we have the video there. Haeckel's rule. So we have Haeckel's rule, and then complete conjugation. Okay, we have conjugation there. Alright, so we'll end here for this tutorial, and then remember to check our playlist for the next video on aromaticity, where we are going to talk about these factors or how we can determine whether a compound is an aromatic or not. And don't forget to subscribe and share this video with your colleagues. Thank you.